Chapter 16 will be split into 2 days of notes videos with the first day focusing on probability distributions. When we're dealing with a random event that can take on a number of different values, we assign it a random variable. And we use a capital letter like capital X to denote the fact that this can take on a number of different values. If you see that same letter in lowercase, like we do here, that means we're talking about a specific instance of this random variable. Take, for example, rolling 2 dice. The capital X would represent the sum when we roll these 2 dice and the fact that it could equal anything between 2 and 12. Lowercase x would represent a specific situation, such as rolling 7 when we roll 2 dice. There are 2 types of random variables, discrete and continuous. You might remember these back from Unit 1. A discrete random variable can take on a countable number of distinct outcomes, such as the number of eggs a hen can lay, number of touchdowns scored in a football game, number of students in a class. We can have 20 students or 21 students, but we can't have 20.357. Continuous is the opposite of that. If we were to pour milk into a glass, it doesn't just automatically jump from 2 ounces to 3 ounces of milk. As the glass fills, it occupies every value in between 2 and 3. So in this first day of Chapter 16 notes, we're going to focus on probability distributions. Here's an example of one showing the distribution for the random variable x, which represents the outcome of a single die roll. Underneath that, we have the probability. We can see in this table we have all the outcomes of rolling a die, 1 through 6, and the probability associated with each of those outcomes, 1/6 chance for each of these. One of the most common questions that you'll be asked for a probability distribution is to find the expected value. This just wants you to find the mean. So we can find it using this equation right here. This variable represents the mean. This is how we represent expected value without actually writing it out. Here's our equation, sum of x times p of x. So we just take each outcome in our probability distribution, we multiply it by its corresponding probability. All of those get added together, and that gives us our mean. One other note, in every probability distribution, all of our probabilities should total exactly 100%, or 1. So in this question here, we have a person bringing their car into a mechanic for a problem with the air conditioner, and the mechanic tells them that there's really 2 things that they can do. They can recharge the coolant. 75% of the time this is going to work, and it's only going to cost $60. However, if it doesn't work, they need to replace the entire control unit, and that's going to cost an additional $140. So we were asked a number of questions about this, but the first is to define the random variable and construct the probability model. A probability model and a probability distribution are the same thing, so we want to start off by making this table. And first, we want to define our random variable. The random variable is what the random event is, and for this problem, it's the cost of this repair. Okay, so we have 2 outcomes. Each has their own corresponding probability. The first outcome was that we would just recharge the coolant. That cost $60. The other outcome was that we would have to replace the whole unit. That was at an additional $140. Okay, that's in addition to the $60 to recharge the coolant, which has already been done. So the total cost for replacing the unit is $200. All right, each of those had their own probability. It told us there's a 75% chance that recharging the coolant would work, which means there's a 25% chance that we would have to replace the entire unit. That's our distribution, or a probability model. We want to find the expected value, or the mean cost of this repair. So to find that, we just take each individual outcome and multiply it by its probability. Those all get added together. So we have 60 times 0.75 plus 200 times 0.25, and the expected value, or the mean repair cost, is $95. As for what this means in this context, it means that car owners with this problem will spend an average of $95 to get it fixed. Note that no one actually pays $95. You either pay $60 or you pay $200. This is just the long-term average if a lot of people were to go into the mechanic with this problem. Finding the expected value is finding the center of the probability distribution, and we always want to talk about spread as well. So we also want to find the standard deviation. And to find the standard deviation, we're going to start off by finding the variance. It's just what we have to do along the way to getting towards that standard deviation. Variance is given by this equation, and we want to take each individual x value, subtract the mean, square that difference, and then multiply it by its probability. So we do that with every column in the table, and then we would take the sum of all those values. That's the variance. To find the standard deviation, we just take the square root of whatever the variance is. So let's go back to this repair problem. At this point, we know that the mean is $95, and let's use that to find the variance. So here's our equation for variance. For each of these columns, we're going to take the repair costs, subtract the mean, square it, multiply by the probability. So 60 minus that mean of 95 squared times 0.75. Same thing for replacing the control unit at a cost of $200. Add those all up, and we get a variance of $3,675. To find the standard deviation, we're now just going to square root this number. So standard deviation is 60.62 or $60.62. What does that mean in this context? Repair costs will vary from the mean of $95 by an average of 60.62, $60.62. So let's wrap up with this example here. To play a game, you must pay $5 for each play. There's a 10% chance you will win $10, a 40% chance you will win $7, and a 50% chance you will win only $3. So to start, we want to make the probability model. The random variable for this problem is going to be the amount won, or the profit. Keep in mind that when we play this game, we're paying $5 to play, which means when we win $10, we have to subtract the $5 from that. So we have x equals amount won, and then there's the three outcomes, 10, 7, and 3. But for each of those, we're going to subtract the $5 that it cost to actually play the game. So the amount that we're actually winning would be $5, $2, or losing $2 in that last case. Each of those has their own probabilities. This would be our probability distribution. Part B, find the expected value. This is the mean. We want to take each of these situations, multiply their outcome with their probability, add them all up. So the expected value for a single play would be 30 cents. Standard deviation, now we're going to take each of these individual outcomes, subtract the mean of 30 cents, and then square it, multiply it by the probability. So that gives us 6.01. Now I wrote this over here just to note, okay, that when we're dealing with variance, we're dealing with square units. So this is really 6.01 square dollars. It's a concept that doesn't really make sense. That's why we don't use variance. We want to square root this to get to the standard deviation of $2.45. Part D, you have $1,000. Would it be smart to play this game? It would. Reason being, our expected value is positive. We're expected to win money if we play this game. If we have a large enough bankroll, okay, considering the standard deviation is a lot larger than what we're winning, there's going to be some swings in our wins and losses, but if we have enough money to survive those swings, we should make money over the long run.